So the mole is a topic that you do in Year 11 chemistry, and it's kind of the way that chemists count atoms, and they use moles to represent however many atoms they actually have. Now, we need to standardize a version of what a mole actually is. Now, just like a dozen is standardized to be 12, is known to be 12, 1 mole is known to be 6.02 times 10 to the power of 23 of something. So it's a very, very large number. Why is it such a large number? Well, it's because atoms are so small, and we need a nice way of saying how many we have. So these two equations here are ones that you'll see in terms of calculations, and it's just a way of going from however many particles you have into however many moles of something you have. The capital N here represents individual particles. The little n represents however many moles of those particles you have. And I'll explain these two down here, and then I'll come back to it, I think. So the first question here is: a cup of water contains 2.5 times 10 to the power of 24 molecules of water. How many mole of water are there? Well, if I want to know how many mole of water, I'll first of all write down little n of H2O, because I want number of moles of H2O. Now, obviously, this is however many individual molecules of water I have. What is a mole? A mole is 6.02 times 10 to the power of 23 of something. So therefore, I want to know how many times does 6.02 times 10 to the power of 23 go into this. So however many groups of 6.02 times 10 to the power of 23 I can get out of this. So I'll go 2.5 times 10 to the power of 24 divided by 6.02 times 10 to the power of 23. That's going to give me how many mole I have, because I want to know how many mole are going to go into the molecules I have. So I'll quickly do that on my calculator here, which is going to be 2.5 times 10 to the power of 24 divided by bracket 6.02 times 10 to the power of 23, and that's going to give me a number of 4.15 mole, and that's however many mole of water are present in 2.5 times 10 to the power of 24. Now, looking at the calculation I've done here, it kind of makes sense. What I've done is I've taken how many individual particles I have, and I've divided that by Avogadro's number, which is what a mole actually is. And that's how I get my equation here. So in my next video, I'll do this particular question here. So I actually stuffed up recording this one, but I've done it here. Let's have a look at my calculation. Determine the amount of individual carbon atoms in 4 moles of carbon. Well, what does this question want me to know? It makes me want to know however many individual carbon atoms in 4 moles. What is a mole? 1 mole is 6.02 times 10 to the power of 23. We defined that before in our last question. So if I want to know what 4 moles is, I need 4 groups of this. So I'll take 4 moles times 6.02 times 10 to the power of 23. I put that into my calculator, and I got 2.4 times 10 to the power of 24. Kind of hard to see that here. And that's my answer for however many individual carbon atoms there are in 4 moles of carbon. Now, if I have a quick look at my calculation here, I can see that my number of individual atoms, which is capital N, that was equal to my number of moles times by what a mole actually is. And that's where we get this equation here. In chemistry, it's really nice to be able to be aware of what calculation you're actually doing. Rather than just banging random numbers into a calculator, always, when you're doing calculations in chemistry, think about what the calculation you're actually doing is. And that's why I'm stressing it here. These questions might be really, really straightforward and simple, but the key thing is, at some point, try in your studies to break down what you're actually trying to do, and make sure when you're putting numbers together, you know why they're going together.